Okay, this is lesson 5.4 on modeling and optimization. So the idea is that now we're going to apply more of our derivative into something that's more applicable. So these word problem situation is where we are going to see how the first derivative is going to apply to a real life situation. Okay, so the first problem here says an open top box is to be made by cutting congruent squares of side length x from the corners of a 25 by 30 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? So first of all, draw a diagram of the situation, right? So you have a rectangle sheet of tin. So it's a rectangle sheet that was originally 25 inches by 30 inches. What you're going to do is you're going to cut out squares, the same size squares, cut out x squares on all four corners. And so the idea is that you bend up this way, bend this side up, and bend this side up, bend this side up, and bend this side up to create an open box, open top box. So your box will look something like this, standing up. Like so, right? So again, there's no cover on the top. And the reason for cutting out the squares so there's no overlap in your material. Okay, so now what we are going to explore is what is the dimension of this, what are the dimensions of this box, right? So this right here, this length is right here, this length right here. So that would be 25 minus the 2x's you cut out. This width right here is this part. That would be 30 inches minus the 2x's you cut out. And then the height of my box here is x, is however large that square you cut out to be. So the volume of this, the volume function of this will be length times width times height, or base area times height, however you want to remember your formula from the past, right? And in this case, I would strongly recommend to just multiply this out and get it into a standard form. So that would give you 4x cubed minus 110x squared plus 750x, okay? And then, because we're trying to maximize the volume, how do we get maximums? We take the first derivative and set it equal to 0, right? So we take the first derivative, v prime of x, that's 12x squared minus 220x plus 750. And we find the maximum by setting this equal to 0. And at the same time, you can see that the coefficients are all even, so we can divide it by 2 just to get the numbers a little bit smaller. So 6x squared minus 110x plus 375. This is not factorable, so we're going to have to use the good old quadratic formula to solve for this. So you get x equals 110 plus or minus 110 squared minus 4 times 6 is 24 times 375 all over 12, which is 110 plus or minus root 3100 all over 12. And you'll get two answers. You get 4.527 and 13.806, right? And you know that because this is the side length that we're cutting into the box, you cannot cut 13 right here, because if you plug that in, you will actually get 25 minus 26. You don't have enough to cut out. So the big number goes away. Our true answer, the size of the square, will be 4.527. So the dimension of the square, so the square is 4.527 inches, right? Because square is the same on all sides, so you can just mention one of the sides. And then your maximum volume, you plug the x in here, into this function right here. So plugging 4.527 into that function, you'll get the maximum volume to be roughly 1,512.04 cubic inches, all right? Now, sometimes the question will ask you for the dimension. If it's asking for the dimension, you simply plug it into here, here, here to get your length, width, and height, and that'll be the dimension of the box, okay? All right, number 2, you have been asked to design a 2-liter soda can. What dimensions will use the least material, ignoring the thickness of the material and the waste in manufacturing? So 2 things you want to do. First thing is you want to assume that the soda can is a cylinder, right? So a soda can is going to be a cylinder. In a cylinder, 2 units you want the radius and you want the height, all right? Now, what do we know? We know the volume of this. So another piece of information we need to know is 2 liters. 2 liters is really 2,000 milliliters, and that actually converts to 2,000 cubic centimeters. So we just now went from volume to volume, but now we can use that volume of centimeters cubed to do our unit measure, right? So the volume of this is 2,000 cubic centimeters, and the volume of a cylinder is pi r squared h, right? Pi r squared, our base area, times the height. So 2,000 equals pi r squared h. You basically are using this given equation, this given information, to solve for one of the variables, because right now you have r and you have h. That's too many variables. Usually I go with the one that's least work, so I solve for h. I try to get h by itself. So h is 2,000 over pi r squared. Okay, now shift gear. We're asking for using the material. So the material used to create the cylinder is surface area. So it's basically a circle and a rectangle and a circle, right? That's the surface. That's the material used to create the cylinder without any waste, meaning no overlaps, right? So the area of this is 2 pi r squared, because you have 2 circles, plus 2 pi r, that's your circumference right here, 2 pi r, times the height, that's your rectangle piece, okay? And see, I have 2 variables again, but I was able to get h by itself in the previous section, so I can go ahead and take this h and plug it back in here. So 2 pi r squared plus 2 pi r times the h I just got, so 2,000 over pi r squared. Okay, now I have a nice equation here. Go ahead and clean this up. 2 pi r squared plus, the pi's are reduced out, one of the r's reduces out, plus 4,000 over r. Because I know I'm trying to minimize the material used, then I know I need to use derivative. So what I'm going to do is I'm going to rewrite this so it's a little bit easier to tackle. 2 pi r squared plus 4,000 r to the negative 1. So that way I don't need to worry about that negative exponent there. Okay, so to minimize this, I find the derivative. So a prime equals 4 pi r, because I take the derivative of with respect to r, and then minus 4,000 r to negative 2. Okay, so it's 4 pi r minus 4,000 over r squared set equal to 0. And same as before, same as in the previous lesson, we're going to write this as one fraction before we start solving. So to write one fraction, you simply multiply the left side by r squared times r squared, so r squared over r squared to make a common denominator. So I get 4 pi r cubed minus 4,000 all over r squared, right? And now we know the denominator will not give us a true maximum or minimum, because the denominator usually gives us the vertical tangent or the cusp. So we can go ahead and just ignore the denominator when we're solving for optimization, just solve for the numerator. So 0 equals 4 pi r cubed minus 4,000. So 4,000 equals 4 pi r cubed. 1,000 equals pi r cubed. 1,000 over pi equals r cubed. If I cube root everything, I get 10 over cube root of pi equals my radius. Okay, let's check the question. It says, what dimension? So I need the radius and I need the height. Once I have the radius, I go back to this awesome formula right here that had the height, so I can go ahead and figure out what the height is. So height is equal to 2,000 over pi times radius squared. Well, radius is 10 over cube root of pi. Okay, so there's a lot of algebra here to clean up, and it actually cleans up pretty nicely, all things considered. So 2,000 over pi, I get 100 pi to the 2/3, right? And now I'm going to reduce out. This is a pi to the 1 and pi to 2/3. So this will reduce out this a little bit, leaving me with 2,000 over pi to the 1/3 divided by 100. So then use these two to reduce out. I get 20 over cube root of pi. Okay, so now I can see I have my height, I have my radius. So my dimension, radius is 10 over cube root of pi centimeters. Height is 20 over cube root of pi centimeters. And that together will give you the least material possible for this. Now, of course, there's always the argument of how do you know this is the minimum and not the maximum? Generally, in these type of situations, it's one, right? It's one answer, not either or. But you could double check by taking the second derivative and plugging this value in, this x value of 10 over cube root of pi to see if it truly is a maximum or minimum based on the concavity of your graph. Okay, so that's a good check for you. Okay, so here's a situation where you actually have two answers. So it says here, we have two possible scenarios here. So maybe break your paper in half so you can have part A and part B. All right, so part A and part B. So it says the sum of two non-negative numbers is 24. Find the numbers if, scenario A, the sum of their squares is as large as possible, so you find the maximum of the sum of their squares, and as small as possible, so you're finding a minimum of the squares. Okay, now, two things you want to talk about. Two non-negative numbers, so x plus y is 24. Using this information, I can say y is equal to 24 minus x. They have to be non-negative, so the x has to be greater than 0 and less than 24. It can't be less than any other numbers, right? So you have a restriction on your domain. Okay, so now let's see the sum of their squares. So the sum is equal to the two numbers squared, so x squared plus y squared, right? And because we have two variables here, I'm going to substitute that second one with 24 minus x. That's my square. That's my y value, right? So I'm going to clean this up. I get x squared plus, really easy to do the work, sorry, 576 minus 48x plus x squared. So it's 2x squared minus 48x plus 576. So take the derivative because we're trying to maximize or minimize. S prime is 4x minus 48, set it equal to 0. X equals 12. Okay. Now we do have a boundary. This is a closed interval. So you have a beginning and the end. So you have to check your end points whenever you have these closed intervals. So I'm going to check and see which ones give me a maximum, which ones gives me a min, right? So I have to check S of 0 because that's one of my endpoints there, 0. And I'm going to check S of 12 because that's my max or min based on this first derivative test, right? And then plug in S of 24 because that's the other end of my endpoint. And you're going to plug it in to this function right here because that's your S function, that's your sum function. So if I plug in 0, I get 0 squared plus 24 squared, which is 576. Okay, good. If I plug in 12, I get 12 squared plus 24 minus 12 is 12 squared. 144 plus 144 is 288. Okay. If I plug in 24, I get 24 squared plus 0 squared, which is 576. So it actually works out perfectly because if the number, since two non-negative numbers add up to be 24, if one of my number is 0, the other number must be 24. And that's why those two gave me the same exact answer. And then if one of my number is 12, the other one must be 12 because 12 plus 12 equals 24. So to answer my question, I would say largest sum of 576 with the numbers 0 and 24. Doesn't matter which one's first, which one's second. And I get the smallest sum of 288 with the two numbers 12 and 12. Okay, so those are my two non-negative numbers that add up to 24. Okay, continuing, the next scenario says one number plus the square root of the other is as large as possible and or is as small as possible. So I have my sum, my new function, is one number plus the square root of the other, and we'll get the maximum and the minimum. Okay, so I get x plus root 24 minus x, because that's what y is, right? Okay, now I take the derivative, because I was trying to maximize or minimize this. So derivative of this is s prime plus 1/2 24 minus x, and negative 1/2. Don't forget chain rule, you have 24 minus x inside, so negative 1 is your derivative inside. So you get 1 minus 1 over 2 root 24 minus x, and you set equal to 0. Since there's no common denominator, I'm going to crisscross applesauce this to make a one fraction. So 2 root 24 minus x minus 1 all over 2 root 24 minus x. And like I said before, this is an optimization problem, so we don't have to solve for the denominator, we just care about the top. So 0 equals 2 root 24 minus x minus 1, add the 1 over, so divide by 2, square both sides, and you subtract, you get a very lovely answer of 95 over 4. Right, so 95 So 95, 98. Sorry, 24 times 4 is 90. Hey, 24 times 4. My math is terrible. Okay, sorry about this. Let me see. I get 24 times 4 is 96. Yes, 95 over 4. Okay, good. Sorry, I was reading something wrong. Okay, and then since that is your number, you got to plug it back in. And same thing as before, we got to check our endpoints. So sum of 0, S of 0, that's one of my endpoint. S of 95 over 4, and S of 24. I plug in 0, right, into this equation right here. 0 plus root 24 minus 0, so I get my answer of root 24. Okay, not too bad. If I plug in 24, I get 24 plus root 0, so that I get 24 here. So those two are not too bad. 95 over 4, I get 95 over 4 plus 24 minus 24 minus 95 over 4 is 1/4. Square root of 1/4 is 1/2. This will give me 97 over 4. Okay, so this one's a little over 24. This one's definitely smaller than that. And this is the smallest one. So your smallest sum is root 24, which is 2 root 6, right? So now you finally answer the question. You say the smallest sum of 2 root 6 with the numbers 0 and 24. Right, 0 and 24 here. This one, it doesn't matter which one's the first, so the second one is the one in the square root. Okay, so you might want to take a minute to mention that. And then you have the largest sum, cannot spell, largest sum of 97 over 4 with the numbers 95 over 4 and the other number to be 1/4 because they need to add up to 24. Okay. All right. So this is one of those rare ones that actually has two answers, both maximum minimums, but it's very good practice. Okay. All right. Last one says, a 216 square meters rectangular pea patch is to be enclosed by a fence divided into 2 equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? Okay, so first thing you want to make sure you see the picture is you have this rectangular patch that got cut in half. Now you cut vertically in half or horizontally in half, it really doesn't matter, but it got cut in half, okay? And you know that this area, this region here, this area is 216, right? So that is 216 meters squared. Now, what are the fences? What are the sides that created this? So for me, all horizontal is X, all vertical is Y. And in this case, I actually will divide it up to be X, 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 Y, Y, Y. I just find this to be a little bit easier to work with the smaller chunks. So the original area given to me, area in this picture will be 2X times Y, because the base times height. And based on the information given to me is 216 equals 2X times Y. So I'm going to use this naturally to solve for y. Y equals 216 over 2x. So 108 over x will be my y value, to replace my y value. So 216 over 2x. Okay. All right, now we're looking at the fencing. So how big is the fencing? Well, fencing has 1, 2, 3, 4. So 4 x's plus 3y. And I want to minimize this, right? But before I minimize, I want to replace that y with the same variable. So that's one variable equation. So you get 4x plus 3 times y. My y is 108 over x. So my function for fencing is 4x plus 324x to negative 1. And you know why I'm doing that, because then it's easier to take the derivative. Okay. All right. So now I take the derivative. F prime equals 4 minus 324x to negative 2. So 4 minus 324 over x squared. Common denominator this. So with x squared over x squared, so I get 4x squared minus 324 over x squared, set equal to 0. And again, since it's optimization, I only deal with the numerator. So 324 equals 4x squared, 81 equals x squared. X equals plus or minus 9, but since this is a dimension, so we're using 9, right? It's a positive answer, okay? So now, if x is 9, right, what is y? So y is 108 divided by 9, y is 12. but it says what dimension for the outer rectangle. So the outer rectangle is 2 of the x's, so that's 18, and the y is 12. So the outer dimension is 18 meters. 18 meters by 12 meters, right? And then the fencing needed. So the fencing needed, you need 4x plus 3y. So we're going back to this equation here, 4x plus 3y. So you will say 4 times 9 plus 3 times 12. That's 36 plus 36. You need a total of 72 meters for your total fencing. Okay? And all right, that's it.